So how is everybody? I missed you. Haven't seen you for a week. Did you have a good President's Day weekend? Celebrate our presidents? Okay, well, we have a lot to do today because of the holiday. No such thing as a holiday in this business, you know. It's kind of like the garbage men. If Monday is a holiday, then the people who get their garbage picked up on Monday have their garbage picked up on Tuesday, just like the people who have their garbage picked up on Tuesday. So if you're a garbage man, a holiday just means you work twice as hard on one of the days and you get one day off. So today we have to do two sections of the textbook. We have to do section 2.4 and 2.5. So normally what I would do in 2 class days, I want to do today in 1. Luckily, because I have the slides, I can include the explanations and a lot more sample problems. Those will be on the slides. So I won't do everything which is on the slides today, but I will put up the full slideshow. You'll get the benefit of a full hour's worth of class on the slides. So we're going to look today at the product rule and the quotient rule and the chain rule. The product rule and the quotient rule are what we'll do first. That's from section 2.4. And they resolve the question about how do we find the derivative of a product of two functions if we know the derivatives of those functions to begin with. And the same thing for the quotient. So let's remember what we did last time, a whole week ago, about derivatives of combinations of functions. We learned something that we call the sum rule, that if you have two functions, u and v, then the derivative of the sum of those two functions is the sum of the derivatives of those two functions. And it has a nice ring to it. The derivative of the sum is the sum of the derivatives. Likewise, the derivative of a difference of two functions is the difference of the derivatives of those two functions. And if you take a function and multiply it by a constant, then the derivative multiplies by the same constant. So that brings us to the question, what would happen to the derivative of a product of two functions? Well, Leibniz, who was one of the first people to write down all these rules for differentiation, thought that it stood to reason that if the derivative of a sum is the sum of the derivatives and the derivative of a difference is the difference of the derivatives, then the derivative of the product should also be the product of the derivatives. Okay? So that's a conjecture there. Is it true that the derivative of a product of two functions is the product of the derivatives of the two functions? And actually, it doesn't take too much time to look and find that this isn't true at all. If you take a simple example, like one function x and the other function x squared, then you can test whether this is true. You can test whether the derivative of the product is the product of the derivatives. What is the product of the two functions? It's x cubed, and the derivative of x cubed is 3x squared. But the derivative of u is 1, and the derivative of v is 2x. The product of those two is 2x. 3x squared is not the same function as 2x. Okay, so because it's not true in this particular counterexample, we don't have a rule like this. Okay, it might be true in some very special cases, but as a rule, the derivative of the product of two functions is not the product of the derivatives of those two functions. So, too bad for Leibniz. Instead, we have to think more carefully about what it means to change both factors in a product. Okay, so to do that, let's do a tasty example here. Let's say you work in some fast food joint making delicious hamburgers, and you want to make more money. Do you want to make more money? Sure, we all want to make more money. How would you make more money working as a fry cook here in your fast food joint? Well, basically, you have two choices. One is that you work longer hours. Right? Instead of working 8 hours a week, you work 10 hours a week. Or you can convince your boss to give you a raise. Those are all the legal methods of making more money working at this burger joint. You could probably steal money from the till or something more nefarious, but basically, this is what it is. If you get a 25-cent raise in your wages and work 5 hours more per week, then you have changed both your wage and your hours. Right? You work longer and you're making more money per hour. How much more money do you take home each week? Well, the change in your wages is 25 cents. The change in your hours is 5 more hours per week. Is it true then that the change in the income is the change in the hours times the change in your wage? That is, if you make 25 more cents per hour and you work 5 more hours than you did before, is the change in your take-home pay $1.25? No, that seems pretty low. right? What else can you say that's bad about this rule? Well, changing either one of these things independently should change my income. If I just get a raise and don't get more hours, I should still make more money. Or if I just get more hours without a raise, I should still make more money. But with this formula, if either one of these things is 0, if I don't change my hours or I don't change my wage, then I wouldn't make any extra money. And so that's why this isn't realistic. Okay, so what is realistic? Well, let's think about the changing the factors in a product. The change in my income is the product of my new wages times my new hours minus the product of my old wages and my old hours. So if I get a raise of delta W, W is wages, delta W means changes in wages, and I work delta H more hours, H for hours, delta for change in hours, then this is my new income, this is my old income. Expanding that out, what do I have? Well, this is W times H, W times delta W times H, and then delta W, delta H. So this was the only term we were looking at before, your raise times your change in hours. But there's lots more going on when you change both factors in a product. Subtracting off the original product, what we get is a difference of W times delta H plus delta W times H plus delta W times delta H. Make sense? Okay. Now what does this have to do with derivatives? I thought we were doing calculus. Okay. Well, we'll see. Let's take a look at a picture geometrically. If you think about income as the product of wages and height and hours, then you can draw a rectangle where wages is the width and hours is the height. And then the area of the whole rectangle represents our new income. The area of the darker rectangle represents our old income. And what's outside the smaller rectangle and inside the bigger rectangle represents new money, new income. And as you see, we've got W times delta H, delta W times H, and delta W times delta H. And of those three little pieces that make up the change in income, the one which is just the product of the two changes, that's actually the smallest of the three. Okay, so there's a lot more going on besides just the product of the changes. You have the other two factors, other two terms in the change in income. Okay. So now let's think about derivatives. Let's consider that our wages and our hours are continuous functions over time, and so that makes our income continuous over time, and we can ask ourselves what the change of income as a function of time would be. To do that, we would take that delta I divided by a small change in time, delta t. Okay? Replacing delta I with this expression that we figured out before, W times delta H plus H times delta W plus delta W times delta H. Dividing that by delta t gives us a sum of three fractions. We have W times delta H divided by delta t, H times delta W divided by delta t, and then delta W times delta H divided by delta t. Now what's going to happen to these as we let delta t go to 0? We would let delta t go to 0 if we wanted to take the derivative of the income function, the derivative of the product of wages and hours. And if we were to do that, well, here we have a difference quotient, and the limit of the difference quotient would be a derivative. What derivative would be represented here? H prime of t, or in Leibniz notation, dH divided by dt. Likewise, this would be dw dt. And what would happen here? Well, this term becomes dH dt again, but we're multiplying it by delta w. And what happens to delta w as delta t goes to 0? What happens to delta w as delta t goes to 0? What's your gesture? Goes to infinity. I'm not thinking about delta t. I'm thinking about delta w. Okay. If we assume that w is a continuous function, then a small change in t should make a small change in w. And the smaller the change in t, the smaller the change in w. And so the limit as delta t goes to 0 of delta w just by itself is 0, which means that this term is 0 times dH dt. So all told, we have w dH dt plus h dw dt times something which in the limit, plus something which in the limit is 0. Okay, so that smallest term, the product of the two changes, goes to 0 when we take the limit, leaving us with these two terms here. W times the rate of change of hours plus hours times the rate of change of wages. So to summarize, what we've proven, without thinking about specific applications, what we've shown is that the derivative of a product of two functions u and v can be written as u times the derivative of v plus the derivative of u times v. Okay? uv prime plus u prime v. Or if you like Leibniz notation, the derivative of uv is du dx times v plus u times dv dx. Okay, so this is called the product rule, naturally, because we're using it to find the derivative of a product. Also sometimes called the Leibniz rule, because Leibniz was the one who figured it out for the first time. Okay? So it's not the derivative of a product is the product of the derivatives. Instead, it's a more complicated rule, but at least there's a rule. I mean, we should be thankful that there is a method to find the derivative of a product. Now, the example that we used to disprove the naive product rule, the idea that the derivative of the product would be the product of the derivatives, was that we could try with x and x squared, and it didn't work out the way we thought it might. So let's use this newfangled product rule and double check that we do get the same answer. Okay? Well, if u is x and v is x squared, then u times v is x cubed, and I would hope that this product rule would result in 3x squared. Well, u is x, v prime is 2x, u prime is 1, and v is x squared. So the first term is x times 2x. The second term is 1 times x squared. So it's 2x squared plus 1x squared. Aha, they add up to 3x squared. And that's what we would get doing it the regular way. Okay, so at least we've shown that the product rule is consistent with other rules for differentiation. Make sense? Okay, now that's not a very useful application of the product rule because we wouldn't want to do a polynomial like factoring it as x times x squared. Instead, we might try it on other examples such as this one. Here's a nasty product of polynomials. 3 minus x squared times x cubed minus x plus 1. Okay, now this is just a polynomial, so we could multiply it all out and take the derivative term by term. And if we did that, multiplying it all out would give me negative 5x to the fifth, no, negative x to the fifth plus 4x cubed minus x squared minus 3x plus 3. And then we could just differentiate it using our friend, the power rule, right? Negative 5x to the fourth plus 12x squared minus 2x minus 3. And then that term goes away. Right? And that much we know. What would happen if we tried instead to do it with the product rule? If you were copying down the power rule way, I'll go back to it in a second. But if we do it with the product rule, we have two factors, 3 minus x squared and x cubed minus x plus 1. We'll take the derivative of the first times the second plus the first times the derivative of the second. And then here's what we would get. Well, negative 2x is the derivative of 3 minus x squared. Copy the x cubed minus x plus 1. 3 minus x squared stays where it's at, and then we take the derivative of x cubed minus x plus 1, which is 3x squared minus 1. Okay, so stepping down step by step. Now we should really check that this gets the same thing that we got in the previous example, and if you expand this one and the second one, let's just compare the top degree term here. This is negative 2x to the fourth, and here's a negative x squared times 3x squared, so it's negative 3x to the fourth. Negative 2x to the fourth minus 3x to the fourth does get you negative 5x to the fourth. Okay? And you can do the rest of the foiling. So double checking with what we got on the previous example, it is the exact same thing. Negative 5x to the fourth plus 12x squared minus 2x minus 3. Okay, so which one do you like better? The FOIL it out and then differentiate, or the product rule and then FOIL it out method? How many would rather do FOIL first? Okay, how many would rather do FOIL second? That is, use the product rule first. Okay, so more of you like the product rule first. And the more complicated these polynomials get, the larger the advantage the product rule is going to have over the FOIL it out and use the power rule method. Okay. And then there are examples where I have no choice. All I know is the only choice I have for finding this derivative is to use the product rule. So, for example, to take the derivative of the function which takes x to x sine x, that's a product of the function x and the function sine x. So, I take the derivative of the first function times the second function plus x, the first function x times the derivative of the second function. So it's 1 times sine x plus x times cosine x. And of course, you don't have to write 1 times sine x. You can just say sine x plus x cosine x. Okay, question? Okay. So you know that I'm big fans of mnemonics, and I have a couple of for these. All right. If I think of my two functions as named hi and ho, then the derivative of the product hi ho is ho d hi, hi d ho. Okay. Right? The first one times the derivative of the second plus the second one times the derivative of the first. Ho d hi, hi d ho. Like it? That's why I was playing Cab Calloway at the beginning, because he has the song Minnie the Moocher, which goes hi d ho. Hi, ho. All right. So that'll help you remember the product rule. If you've seen the Blues Brothers, then you know Cab Calloway was in. He played Curtis in the movie. And I'm talking about the original Blues Brothers, not the year 2000 version, which is a cheap imitation. Okay. Questions about Cab Calloway? All right. The YouTube that I posted to the Facebook page and played before class, that was Cab Calloway. Okay. Ho-de hi, hi-de ho. Okay, how would this generalize if you had a product of more than two functions? Well, it turns out that you can apply the product rule in several different ways and use it to find a product rule for iterated products. Okay, say we've got three functions, u, v, and w, and we want to find the derivative of the product of all three of those put together. Well, I can say that this product of three functions is actually a product of two functions, where the first function is called uv, and the second function is called w. So uvw is uv times w. And I can apply the product rule to the two functions uv and w. If I do that, then I get, well, ho d hi, ho d hi, hi d ho. There you go. uv prime times w plus uv times w prime. Now, uv, I can remember now, is a product. So to find its derivative, I can apply the product rule to u and v. And so I get, right, ho d hi, hi d ho, times w. And then that leftover uv w prime is just waiting there. And if I rearrange them like this, in alphabetical order, I see that there's a nice pattern. In each term, I wrote down uvw, 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 three factors, so write it down 3 times. And then I take the derivative of each factor in succession. Okay? And you can see how that might generalize. If I have more than 3, say I have 4 things, then I'll write down all 4 of them, differentiate the first. Write down all 4 again, differentiate the second. Write down all 4, differentiate the third. Write down all 4, differentiate the fourth. So that's how the product rule goes. It looks at the change in each factor of the product separately. Okay? Yes, question?
Why did you split the second UV in line 2?
Why did I split the second UV right here?
Why did you not?
Why did I not? Well, I didn't when I got down to this line. It's just sort of temporary. All right. Now, this is not something I need you to do on a test or a quiz, as long as you remember the result here, that the threefold product can be written that way, or the derivative of the threefold product. I'm just showing how you could derive it from the regular old product rule. Okay, so that's about all I want to say about products for now. Moving on then to quotients. Okay. Well, unfortunately, I don't have a tasty burger-like example for quotients. But we can use what we know about products to find something about quotients. How would we find the derivative of a quotient? Well, if I have two functions, u and v, then I can call their quotient function q, and I'd be interested in knowing what the derivative of q is. I'll figure out the derivative of q by sneaky making it a product instead. Okay? U is equal to q times v. Phones away, please. U is equal to q times v because q is defined to be the quotient of u and v. Okay? Now I've written this quotient instead as a product, or written this quotient equation instead as a product equation, and I can apply the product rule to that equation. That would tell me that u prime is the derivative of qv, that is q prime v plus q v prime. Okay, now where was I going? Well, I wanted to find the derivative of q. Here is the derivative of q, so let me solve this equation with q prime on one side. And if I do that, I would have to take the qv prime, move it over to the left-hand side, and then divide by the factor on q prime, which would be v. Right? That would tell me that q prime is u prime minus qv prime divided by v, which is kind of nasty, but you can write it another way as u prime divided by v minus u divided by v, that's q, v prime divided by v. That's still another way to write it would be u prime v minus v prime u prime v minus uv prime divided by v squared. U prime v minus uv prime divided by v squared, where I'm just taking this expression up here and I'm getting a common denominator. Okay. Now I haven't explained why the quotient of two functions should be differentiable, but it turns out that that is true. It is that if these two functions have a derivative, then the quotient has a derivative, and so the derivative of the quotient is this funny combination, which we'll now call the quotient rule. So just like before, you don't have to memorize the derivation, but it is kind of nice to know that the quotient rule comes from the product rule. It's not some newfangled idea. Okay. So the derivative of a quotient is the derivative of the numerator function times the denominator function minus the numerator function times the derivative of the denominator function divided by the quotient of the denominator, divided by the denominator squared. Okay? Oh, here it is in a nice purple box. Okay? As long as, well, again, you can't use any of these theorems to tell a lie. So if v of x is not 0, then the quotient is differentiable. If v of x is 0, then, hard work. Okay? So how does this resemble the product rule? Well, we did see a similar combination where you have the two factors and you differentiate one in each. The difference here is that we have a minus sign, and that's because there's a difference between the numerator and the denominator of a quotient, much more so than the difference between two factors in a product. Right? If you interchange the factors in the product, you have the same thing. Right? It's still the same function. But if you interchange the numerator and denominator, well, that's a much different function. And so it makes sense that there shouldn't be any kind of symmetry here between u and v. Okay. So let's do a little sanity check on the quotient rule. If we were to apply the quotient rule to a function whose numerator was x squared and whose denominator was x, then we should get the derivative of the function x. That is, we should just get 1. So let's double check that this does give us what we predict would happen. So the derivative of the quotient of u and v is v times the derivative of u, that is the denominator times the derivative of the numerator, minus the numerator times the derivative of the denominator over the denominator squared. Okay, the denominator squared, that's not too hard. X squared is x squared. The derivative of the numerator is 2x. Whoops, sorry. The derivative of the numerator is 2x. The derivative of the denominator is 1. So I've got x times 2x minus x squared times 1 divided by x squared. X times 2x is 2x squared. X squared times 1 is x squared. The difference between 2x squared and x squared is x squared. Divide that by x squared, and we do, in fact, get 1. So it all does work out. That's good. The product rule is not telling us anything that is inconsistent with what we could otherwise find. Okay, but that's not what the product rule, the quotient rule is really good for. It's good for finding derivatives of things that we couldn't ordinarily find. Now there is also a mnemonic for the quotient rule. Because the two pieces of the quotient are, they have significance in their position, I call the numerator high and the denominator low. You're going to miss the best part. He'll never know what the derivative of cosecant is. Plus, he's going to be on video walking out of class. Okay, if the numerator is called high and the denominator is called low, then I can think about the numerator of the derivative of the quotient being low d high minus high d low. Low d high d low, and then the denominator is 2 multiples of low, so it's just low, low. Okay? Low d high d low, 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 and then you have to remember the negative sign there. So building on our previous mnemonic, you could say low d high d low, sine, low, low. You have a nice rhyme? Okay. Low d high minus high d low, draw a line and square the low. There you go, draw a line, square the low. And it does rhyme, that's cool. Do we have any other to share? Maybe we'll do that one next year. Okay. So if we had lots more time, I would get you to practice a few of these. Instead, I'll just walk you through the first one, and then when you go to review class, you can look at the other two on your own time. But in this first example, we have a rational function that's a quotient of two polynomials. How would we find the derivative of 2x plus 5 divided by 3x minus 2? Well, identifying which is high and which is low is pretty easy. This is high and this is low. Okay, I'll want low d high minus high d low divided by, draw a line and square the low. Okay, so let's do that. Here's low, right, 3x minus 2. D high is the derivative of 2x plus 5 minus high, 2x plus 5 left by itself, times d low, the derivative of 3x minus 2, and that gets divided by 3x minus 2 squared. Okay. Now, in this particular case, the numerator and denominator are both polynomials. In fact, they're linear functions, so these derivatives are actually pretty easy. 3x minus 2 times 2 minus 2x plus 5 times 3, because 2 is the derivative of 2x plus 5, and 3 is the derivative of 3x minus 2. And then the denominator stays the same, 3x minus 2 quantity squared. Expand it out, 6x minus 4 minus 6x plus 15. The 6x's cancel. Won't always happen that way, but in this case it does. And what we get is a constant, negative 19 divided by 3x minus 2 quantity squared. Okay? Any questions about that process? If you are learning this process of differentiation for the first time, then the product rule and the quotient rule seem like magic, right? It seems like this magical spell that if you cast it the right way, you'll get the right derivative, but it seems almost too complicated to pronounce. Actually, with practice, it starts to become very simple. Just like finding the derivative of a polynomial using the product rule, you'll learn to sort of hold things in your head and write them down and get the whole product rule, quotient rule thing in order. Okay? Good thing we have a website on which you can do lots and lots of practice problems. I call it WebAssign. Okay. So I won't do these other two examples, but there they go. Whoa. Okay, there are the answers. All right, so when you download the slides after class, you can get all of those. But I do want to show you how we can use the quotient rule to find the derivatives of the trig functions. So far, we know the derivative of sine, and we know the derivative of cosine, and we know that tangent is the quotient of sine and cosine. So now that we know how to find the derivative of a quotient, that was the missing piece, right? Now we can use this to find the derivative of tangent. Okay, so let's go ahead. We'll apply the quotient rule to numerator sine, denominator's cosine. So we want low d high minus high d low. The derivative of cosine is negative sine, and low cosine squared. Okay, now we wouldn't want to stop there because you can multiply this out. You get cosine squared x plus sine squared x. And the fundamental identity relating cosine and sine is that cosine squared plus sine squared equals what? 1. Yeah. So this numerator is just 1. The denominator is cosine squared x. So another way to write the derivative of tangent is to say that it's the square of the secant of x. Secant is the reciprocal of cosine. So the reciprocal of cosine squared is secant squared. So the derivative of tangent is secant squared. Not too bad, right? How would you use this same process to find the derivative of cotangent? Well, if you do it all out, then what you get is something very similar. You get negative 1 over sine squared x. That is, you get negative cosecant squared x. Okay? And why is that? Well, what is cotangent? It's the reciprocal of tangent. It's cosine divided by sine. So you're going to do the derivative of cosine times sine minus sine times the derivative of cosine. And where you got 2 positives, you'll instead get 2 negatives. Okay? So sine times negative sine minus cosine times cosine will give you negative sine squared x minus cosine squared x over sine squared x. That's negative 1 over sine squared x, also known as negative cosecant squared of x. So the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. Secant x you can also find because it's the derivative of 1 over cosine x. Okay, how would you find the derivative of that quotient? Same way we define the derivative of any quotient. What's interesting now is that because the numerator is a constant 1, its derivative is going to be 0. So I have cosine x times 0 minus 1 times negative sine x. That gets divided by cosine squared x. Right? Low. Okay? So you could write that, well, you won't know the derivative of cosecant either. Sine x divided by cosine squared x, that's 1 over cosine x times sine x over cosine x, which you could also write as secant x times tangent x. Okay? Now, actually, what we've learned is that if you're taking the derivative of the reciprocal of a function, then you actually could do it 2 ways. You could use the quotient rule, where the numerator is 1 or the denominator is 0. But notice that you'll take that denominator function, multiply it by 0, and you'll take the derivative of the denominator function and multiply it by 1. So as a nice little takeaway, where's the takeaway? Did I skip the takeaway? Okay, never mind the takeaway, except to say that the derivative of a reciprocal is the derivative of the denominator divided by the denominator squared. Okay, so that's how we got secant x times tangent x. You do the same thing with cosecant, then you'll get negative cosecant x times cotangent x. And you would work it out the same way. So if you put this all together, you get this nice little table. And when I put this table up on the board, people say, oh, do we have to memorize that? And I'll say, no, you don't have to memorize it. You do have to know it, though. And how you choose to know it is up to you. You can memorize those things, or you can see the patterns which appear in this table. Notice that the derivative of sine is cosine, and the derivative of cosine is negative sine. That much we shouldn't have too much trouble remembering. The derivative of tangent is secant squared, and the derivative of cotangent is cosecant squared. Oh, it's actually not cosecant squared, it's negative cosecant squared. The derivative of secant is secant tangent. The derivative of cosecant is cosecant cotangent. So I've got them grouped into blocks of 2, and in each group, I replace the regular functions with their complements, with their co-versions. Derivative of sine is cosine. The derivative of cosine is sine, with a minus sign. The derivative of tangent is secant squared. The derivative of cotangent is cosecant squared, with a minus sign. So as long as you remember that the co-versions have the minuses in there, then you've seen all the patterns. So I guess all you need to remember is these 3 lines and that you can change the functions to their co-functions and insert a minus sign. So fewer things to memorize than you might think. Okay. Last thing I want to say about the quotient rule before moving on is that we can use the quotient rule to prove the power rule for other exponents besides the ones that we already know. So remember that we prove the power rule for positive whole numbers, like 3, 4, 12, 17. Jimmy Stewart has allowed us to use the power rule for any powers, even fractional powers, even irrational powers. But each new rule that we use for differentiation gives us a new perspective on the power rule. For instance, I can use the quotient rule to find the derivative of a power function where the power is a negative whole number, such as negative 3. How would I do that using only things that I have proved already? Well, the derivative of x to the minus n is the derivative of 1 over x to the n. And I can use the quotient rule there. I could say that it's the derivative of 1, which is 0, times x to the n, minus 1 times the derivative of x to the n, divided by x to the n squared. So here I have applied the quotient rule, but I just didn't write the part where I multiplied x to the n by 0. Okay. If n is a positive whole number, then I can use my regular old power rule here. The derivative of x to the n is n times x to the n minus 1. The denominator is x to the n squared. That is x to the 2n. Pretty cool now because I've got my minus n as a factor, and my power of x is n minus 1 minus 2n. What is n minus 1 minus 2n? It's the same thing as minus n minus 1. So the derivative of x to the minus n is minus n, x to the minus n minus 1. Okay, so we established it for, sorry, I keep stepping on your feet. We established it for positive whole number powers using Pascal's triangle. For the power 0, we just proved it from scratch. That was the constant function rule. And for negative whole number powers, we can use the quotient rule. So now we've established the power rule for all integers, positive, negative, or 0. Okay. So that's all we did in this first part. Product rule, quotient rule, derivatives of the trigonometric functions, not just sine and cosine now, but tangent, cotangent, secant, cosecant, and also now power rule for negatives. Okay, so that was one class in 45 minutes. If you have more questions about that, be sure to download the slides and look over some of the things I skipped over. Also in recitation, I gave the TAs a nice worksheet for product and quotient rule. Okay, so I'm going to have to switch the slideshow over so you can just do a little stretch. Twiddle your thumbs if you want. And have pity on me because I have to do this again at 2 o'clock, right? Do rapid fire calculus again. Okay. So what was with that picture on the front here? These are people stamping hams in a factory. The product of how many hams they can produce is how fast they can stamp them times the number of hams which come out. Now I have a little more descriptive background image here. We're going to talk about the chain rule, and here I have a picture of the chain. Okay. All right, you stretched and ready? I didn't see any of you stretch, but we'll just assume you're metaphorically stretched. Your minds are stretched and ready for the chain rule. Okay. So same announcements because we haven't moved since the beginning of class. Okay, now we'll look at the chain rule, which is the way that we find the derivative of a composition of two functions. All right. So let's remind ourselves what the composition of two functions actually means. If we are writing f composed with g at x, what that means is f of g of x. That is, we take x, we apply g to it, and then we apply f to the result. Because functions are like machines, they have an input and an output. So g can take an input x, and it will output g of x. And there's nothing to stop me from taking that output g of x and running it as input to f of x. And what would come out there is the composition f of g of x. What would stop me from doing that? Well, I have to make sure that the range of g is contained, or the output here is contained in the domain of f. But as long as that works, then I can take the output of g, run it as input to f, and those two building blocks together make a new function which I can call the composition f with g. So it's a natural question to find the derivative of the composition and see how it might be based on the derivative of one part of the composition and the derivative of the other part of the composition. Okay, so that's the idea. How do we find the derivative of a composition of two functions given the derivatives of the individual functions? Well, again, I have an analogy. It's not delicious, but it is at least metaphorical. So let's think about riding a bike. We're riding in the Tour to NYU, which doesn't have many hills in it, but that's okay. And we want to go faster. Well, if you've ridden a bike that has multiple speeds, then you know how to go faster. There are a couple of ways. You can pedal faster. Pay no attention to this little message, okay? You can pedal faster, or you can change your gears. Right? And how does a multi-speed bike actually change its gears? Well, there are lots and lots of gears on this front sprocket and lots of gears on this sprocket. Maybe there's, well, lots and lots. There's 2 or 3 gears here, and there's 2 or 3, or maybe 5 or 6 gears here. And the ratio of the circumference of the front gear to the circumference of the rear gear is what determines how fast the back wheel turns around. So to write it in symbols, the angular position of the back wheel, let's call that phi, is a function of the angular position of the front sprocket, we'll call that theta, and the function is just multiplying by the ratio of the radius of the front sprocket to the radius of the back sprocket. So if you increase the radius of the front sprocket, then you're going to be biting out more chain with your revolutions of the front sprocket, which will make the back wheel go faster. If you reduce the radius of the back sprocket, then it will take fewer chain links to turn the back wheel around once as well. So either increasing this or decreasing this will make you go faster. But the major point is that the position of the back wheel depends both on the ratio and the position of the front wheel. So to change the speed of the back wheel, you can change the ratio, or you can change the speed of the front sprocket. And if you double the speed of the front sprocket, your speed will double no matter what. Okay? So that leads you to think that the derivative, or the angular velocity of that back wheel, is going to depend on the angular velocity of the front wheel and also how fast the gear is changing. Okay. So that's the way to think about it heuristically with an analogy. Let's think about it very simply in symbolic terms. Let's suppose our two functions are just plain old linear functions. What can you say about the composition of two linear functions? Well, a linear function just means it multiplies the input by a constant, possibly adds another constant. So f of x is mx plus b. G of x is linear too, so g of x takes a similar form. We can't use m and b anymore because those were used for f, but we can call them m prime and b prime. So f of x is mx plus b, g of x is m prime x plus b prime. What can you say about the composition? Well, if you just formally compose them, f of g of x is m times m prime x plus b prime plus b, because this is m times g of x plus b. G of x is m prime x plus b prime. And if you FOIL this out, well, FOIL I guess is glorified, but if you multiply this out, then you get m times m prime times x plus m times b prime plus b. Who cares? Well, if you look at it formally now, you see that what we have is a constant times x plus another constant, which means that the composition of two linear functions is another linear function. And what is the slope of that composed linear function? It's the product of the slope of the first function and the slope of the second function. So when you take two linear functions, mx plus b, m prime x plus b prime, whatever those are, the slope of the composed linear function is the product of the slopes of the component functions. Okay, so what does that have to do with anything? Well, calculus allows us to treat some nonlinear functions, some complicated functions, as if they were linear functions. We said that the derivative measures the slope of the tangent line, but it also helps create a linear approximation to the function near that point. So to put it another way, if we have one function g of x, which I'll call u just for shorthand, and another function f of u, which I'll call y for shorthand, then I'd like to find the derivative of y as a function of x. That would be the composition of f and g. Well, the definition of the derivative says that f prime is a limit of difference quotients which look like delta y divided by delta x. So limit means that if I take delta x small enough, I can say that f prime of y is approximately a delta y divided by delta x. In other words, delta y is approximately f prime of y times delta u. That's just this equation solved here. And I think I have a typo. Yes, this x here should be a u, because that's a u. Okay, typo there. Now, doing the same thing for g, I have the derivative of g is approximately delta u divided by delta x. So I can solve for delta u as g prime times delta x. Putting those two together, I can say that delta y is f prime of y times delta u. Delta u is g prime, this should be an x, times delta x. And so the quotient delta y divided by delta x can be written as approximately f prime of y times g prime of u. Okay, this is the slope of the tangent line of the first function. This is the slope of the tangent line of the second function. So we're saying that the slope of the tangent line of the composed functions is the product of the slopes of the tangent lines of the component functions. Okay, another way to state that is what we call the chain rule. So the chain rule goes, let f and g be any functions. We have to make sure that g is differentiable at x and f is differentiable at g of x. Then the derivative of the composition f of g at x is f prime of g of x times g prime of x. F prime of g of x times g prime of x. If you like Leibniz notation, you can state it this way. If y is f of u, u is g of x, then the derivative of y as a function of x is the derivative of y as a function of u times the derivative of u as a function of x. Okay, the chain rule is, I would say, one of the most important theorems in the differential part of calculus. It allows us to compute the derivative of a composition. And in fact, much of what we'll do in the rest of Chapter 2 and Chapter 3 and Chapter 4 is going to depend on the chain rule. So I hope that we do understand the chain rule well. Maybe not today, maybe not tomorrow, but soon, and for the rest of the term. So what can we say about the chain rule there? Well, a nice way to put it is that the derivative of the composition is the product of two derivatives. It wasn't true that the derivative of a product was the product of the derivatives, but it is true that the derivative of a composition of two functions is the product of the derivatives of those two functions. The only twist being that these two functions are not evaluated at the same point. It's not true that the derivative of f composed with g at x is f prime of x times g prime of x. Instead, it's f prime at g of x times g prime at x. But that actually makes sense because we don't evaluate f at x. We evaluate f, at g of x. So the derivative of the composition, f composed with g, is f prime evaluated at g of x times g prime evaluated at x. And if you see it decomposed that way, it makes sense that we're chaining f and g together, and we differentiate backwards up the chain. Okay? If you like Leibniz notation, then there's a nice coincidence of notation and intuition. The chain rule looks kind of like cancellation of fractions. We have dy du here, du dx here, and if these were fractions, and these dy and du and dx were numbers, then you could just kind of cancel them like that. It's not actually true, but it does help us to remember how the chain rule works. Okay? Thought bubbles there because we're not allowed to write this, but we can use it to guide our intuition. Make sense? Okay. Very abstract, though, to try to write that out. F prime of g of x times g prime of x. What's that all saying? Well, let's try some examples. We'll see how we can make this come alive. All right. So here we have a function. H of x is the square root of 3x squared plus 1. And we want to find the derivative of h. Okay. If we're going to use the chain rule, then I need to think about making this function a composition of two other functions. And how could I do that? Well, if you just listen to the way that we describe this function, the square root of 3x squared plus 1, then you can actually hear the composition. When I say of there, I'm talking about two different operations and I'm composing them. So the square root of 3x squared plus 1 is the composition of the square root and 3x squared plus 1. Okay? Now, a lot of students want x to be the variable no matter what. So they'll say one of our functions is the square root of x, and the other function is 3x squared plus 1. I sometimes like to keep them separate, so I remember that this function takes as its input the output of the second function, g of x. Okay, so f of u is the square root of u. G of x is 3x squared plus 1. And the function that I'm trying to find the derivative of is the composition of f with g. So let me take those two functions' derivatives and multiply them together. F prime of u, u is the square root of x, which we could write as u to the 1/2. Its derivative is 1/2 u to the minus 1/2. G prime of x is 6x. And so the product is f prime of u times g prime of x. Okay. Now, if you just look at that, you think that's pretty funny looking because it's got a u in it, and the original function only had x's in it. So to put away my toys, I should really return this into a function of x. But that's no problem because I can write u as 3x squared plus 1. So I get 1/2 3x squared plus 1 to the minus 1/2 power times the derivative of 3x squared plus 1, which is 6x. All right. Then I can clean that up a little bit. There's a 6x here and a 1/2 here. They cancel to get 3x. The negative 1/2 power I can write as a square root in the denominator because 1/2 powers are square roots and negative powers are reciprocals. Okay? So basically from this point, I'm pretty much done here. I have written my derivative as a function of x, and this is just cleanup and simplification. Okay, questions about this one? Do we have to simplify? That's a good question that I often get. And the answer is it's going to depend on the context. If we are trying to determine if you understand the chain rule, then really we just want to see, can you multiply this out? Right? So if it's a quiz about the chain rule, then this is all we're looking for. However, there are situations where we will take that derivative and construct an equation with it. And to solve that equation, you will need to simplify the expression. And so it's good to be able to simplify, but only as a means and not as an end. Fair enough? Yes, fair enough. Okay. So a nice corollary that you can take out of the chain rule, which we sort of derived here, is that if you have a generalized power function, that is a function which is a power of another function, then you can find the derivative of that function by taking n times that function to the n minus 1 power times the derivative of that inside function. Okay, that's exactly what I did here because I had 3x squared plus 1 to the 1/2 power. Its derivative was 1/2 3x squared plus 1 to the minus 1/2 power times the derivative of 3x squared plus 1. Okay, so that's just another sort of a generalized version of the power rule. Okay, let's take a look at these two functions, sine of 4x and 4 times sine of x. On the homework, I saw a lot of students who would say, okay, well, sine of 4x, I can just pull the 4 out and write that as 4 times sine of x. And if that were true, then these two functions would have the same derivative. If sine of 4x were equal to 4 sine x, then the derivative of each should be equal to the other. And let's see. Well, in the first one, we're composing u is 4x, and y is sine u. Then dy dx is dy du times du dx. That is, it's cosine u times du dx, which is 4. Cosine u is 4x, 4 is 4, so the answer I get for the derivative of sine of 4x is cosine of 4x times 4. All right, cosine of 4x times 4. Now, the derivative of 4 sine x, in this case, my two functions are the sine function and the multiply by 4 function, but I'm reversing the order in which I'm applying them. So I'm taking sine x, and then I'm multiplying by 4. The derivative of the multiply by 4 function is just the constant function 4, and the derivative of sine x is cosine x, and so I get 4 times cosine x. All right, so if these two functions are the same, then these two functions are the same. Are these two functions the same? Well, if they're the same, then they should be the same at any points I plug in. So what if I plugged in, say, x equals pi over 2? If x is pi over 2, cosine x is 0. Cosine 4x, though, that would be the cosine of 2 pi, which is 1. So these two would not be the same at that point, and so they're not the same function. Okay? The only functions for which you can pull constants out like that, say f of 4x is 4 times f of x, those are linear functions, and sine and cosine are definitely not linear functions. Okay? So don't do that on your homework, because you'll end up with something that's not true. Questions about this one? Okay. All right, so let's kick it up a notch. Yes, order does matter. That's right. Let's take a look at this monster composition here. F of x is, let's see, cube root of x to the 5th minus 2 plus 8 quantity squared. We want to find the derivative. So how many functions are we composing here? Lots, right? Let's see if we can count them. Well, the thing that happens last in our construction is what? The square, okay? And what happens before that? We add an 8, and before that we take a cube root, and before that we subtract 2, and before that we take a 5th power, okay? So some of these functions I can stick together, but as I take the derivative of this function, I am taking the derivative of the component functions in the opposite order. Okay? The outermost function here is the squaring function. So I can use that generalized power rule and say that the derivative of whatever squared is 2 times whatever times the derivative of whatever. The derivative of whatever squared is 2 whatever times d whatever. All right? So I wrote it as u is whatever before, but we can just think about it as any placeholder. Now, am I done? No, because this is still a function, and I still have to take its derivative. And as I look at that function, I see, well, it's got the plus 8. The derivative of plus 8 is nothing. Adding a constant doesn't change the derivative, but I do have to take the derivative of this cube root business. But that's just another power function. So the derivative of the cube root of x to the 5th minus 2 is 1/3 x to the 5th minus 2 to the minus 2/3 power times the derivative of x to the 5th minus 2. Again, this is the generalized power function. The derivative of whatever to the 1/3 power is 1/3 whatever to the minus 2/3 power times the derivative of whatever. In this case, now, whatever is x to the 5th minus 2. And now I'm pretty close to finished because the function I have is a straight-up polynomial. I'm in Happy Town. I love taking derivatives of polynomials. Now I can just say that the derivative is the thing I had before, that thing I had before. The derivative of x to the 5th minus 2 is 5x to the 4th power. Am I done? Yes, now I'm done because there's nothing more to differentiate, right? I've finally differentiated x to the 5th minus 2. It's not a composition of any more functions, and so there's nothing left to differentiate. I can clean this up a little bit. I've got a 2 and a 1/3 and a 5x to the 4th. I can combine those and get 10/3 x to the 4th, but then this term here is not going to change, and this term here is also not going to change. Okay, so just like the power rule, just like the product rule, just like the quotient rule, this is one of those rules that the first time you learn it, makes it seem like magic, especially if you're not writing down all the sub-compositions, letting g be this and f be that, and the derivative of this function and that function. It just seems like you can just let it all flow. And the way you can think about it is it's kind of like an onion, where that outermost function represents a layer of the onion. And as you differentiate, you are unpeeling that onion. You're taking out that outermost layer, multiplied by the derivative of that layer, but you still have a layer inside. So here's the derivative of the outermost layer. Here's the derivative of the next layer. Here's the derivative of the next layer. And now you're actually done. Okay? So you work your way from outside to in, differentiating as you successively peel off these layers. All right? So if you had a function like this, x cubed plus 1 to the 10th power times sine of 4x squared minus 7, what rule would you use first when finding the derivative of this function? Product rule, because we are taking the product of two functions. The last thing we're doing is we're multiplying the function x cubed plus 1 to the 10th power times the function sine of 4x squared minus 7. So when we differentiate, the first thing we're going to apply is the product rule. So what we will want is the derivative of that first factor, x cubed plus 1 to the 10th power, times the second factor left alone, plus the first factor left alone, times the derivative of the second factor. Notice that each of the two factors' derivatives is going to require some more complicated technique of differentiation. In this first case, it is just a polynomial. So I could find x cubed plus 1 to the 10th power and then differentiate term by term. That's a legitimate way to differentiate that function. And in fact, early versions of Mathematica could only do that. They could only multiply out polynomials. How many terms do you have if you were to FOIL out x cubed plus 1 to the 10th power? Ballpark. 1, 5, 100? No, you'd have 11 terms, because you would get x cubed times the, to the power 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and the 0 power. So 11 terms, you could differentiate each by each, or using the power rule generalization, you can take down this power 10, x cubed plus 1 to the 9th power times the derivative of x cubed plus 1, which is 3x squared. Wouldn't you rather do it that way? I would rather do it that way. So first, derivative of the first factor times the second factor, left alone. First factor left alone times the derivative of the second factor. Now that second factor has as its outermost function a sine, so I'm going to write down cosine, and then I'll take the inside function left alone, but then I have to multiply by its derivative, because that's the next layer in the onion, and I get an 8x. So there you have it. I mean, you can clean it up a little bit, but anytime you're multiplying polynomials and trig functions, it's not going to get super simple anyway. Okay, so I don't have any simplifications there written for you. But what's satisfying about the product rule, the quotient rule, and the chain rule is that there is a definite procedure. You can teach a computer how to do all these formal differentiations, and if you can teach a computer to do it, then you can teach a freshman to do it, right? So it shouldn't be too hard to learn these techniques. Before we go, I may have said something which indicated I'm done, but I still have a few minutes left. Let's talk a little bit about related rates of change. There's a whole section about related rates of change, which we're not going to do, but we can think about related rates of change as just an application of the chain rule. So let's think about this. We've got some oil slick that comes out of the ship. You know, the tanker runs aground, and oil starts pouring out of it, and the oil makes a circle as it spreads away from the oil tanker. And we can think about how the change in area, how the area changes as a function of time. Okay, so we know the area of a circle is pi r squared. So if the radius increases, then of course the area is going to increase. How does it explicitly change? The change in area with respect to time is which of these? Is it dA dr, which is 2 pi r? Is it dA dt, that is 2 pi r plus dr dt? Is it dA dt, that is 2 pi r times dr dt, or do we not have enough information to answer this question? How many say the answer is A, 2 pi r? Okay, how many say the answer is B, 2 pi r plus dr dt? How many say the answer is C, 2 pi r times dr dt? And how many say we do not have enough information? Okay, so I don't know if everybody voted, but most people voted for C, and C is correct. All right. Now, what's wrong with A? A is not an incorrect statement. It's true that dAdr is 2 pi r, but the question is asking about the change in area with respect to time. So that's thinking about area changing not as the radius changes, but as time changes. The second one shows that we want to find dA dt, but this is not the right formula for dA dt. This is. It's dAdr times dr dt. Okay, so that's all I have. We learned the chain rule, which helps us find the derivative of a composition. In symbols, you can write it as f composed with g prime is f prime of g of x times g prime of x. And remember, calculus is like an onion, but not because it makes you cry. All right, have a good weekend. I will see you back here on Monday.